Meenakshi. So today's will be lightweight. It's not heavy duty machine learning. It's machine learning in the discrete world. So I've been in Triple IT for about 9 years. This July I'll finish 9 years. Before that I was working for Honeywell. I work in areas like software testing, formal methods, model-based development. So this is the kind of machine learning that people like us use. Everybody wants to do machine learning, so we also said we'll latch on to machine learning, but not the serious kind that involves other entities. So I presume most of you have a computer science degree or pursuing a computer science degree. So you would have done a course called Automata theory of computation, that not so good course which is full of theory and you don't want to learn anything because it's not useful, somehow pass. So this is about that. So this is about learning regular languages. So regular languages are those that are accepted by finite state machines. So you can apply machine learning to learn a regular language, play it like a learning algorithm. So that's what I will do in the morning today. Most of the morning we'll learn algorithms to learn regular sets. So I'll give you a brief background on finite state automata. In case you've not done it, it will be useful. And if you've done it, it will be a quick recap of what it is, just to refresh your memory. And then we'll do a classical algorithm by Dana Angulin on learning regular languages. What is the use? Why would I want to learn a regular language? It's all theory anyway. So that might be a very natural question to ask. So learning regular languages forms a very important problem in program verification. So I'll tell you that briefly. So we look at Anglin's algorithm, and sometime either before lunch or after lunch, I'll also teach you another discrete math related learning algorithm, which is learning based on decision trees. So that's another popular learning algorithm in the pool of learning algorithms that exists. And these two are very closely related because they both involve a lot of logic, very simple discrete maths. And if you learn one, it's very easy to learn the other. And in the last session of today, your TA, Mrs. Amina, she's doing her PhD here. So she will do a tutorial by which, so there are very popular decision tree learning algorithms available. Two most popular ones are ID3 and C4.5. Both are by a person called Ross Quinlan. So we'll do a tutorial session on ID3. I believe you all have Python libraries installed, and she's got 2-3 assignments for you on using and getting ID3 to up and run to learn decision trees. So I'll begin with learning regular sets today. So why do we want to learn a regular set? Why is it important? One is it's theoretically interesting. It's a nice result. And the other thing is it forms the basis of learning invariants about programs. So I'll come to that. But independently, finite state automata, which accept regular sets, are a very robust class of computation models. So you typically, in a course like automata theory, you learn finite state automata. You would know it as DFA, NFA, and things like that. Then you would learn push down automata and context free languages. And if there is time, you would also learn Turing machines. So roughly speaking, they all represent mathematical models that involve computation, that say what we can program and what we can't program. Any problem that you can solve using an algorithm that takes logarithmic time or logarithmic space, log time, log space algorithms can all be done by using finite state automata. A classical example would be parity checking for parity in a binary string, even odd parity. Another example would be doing mod division. I can do mod 3, mod 4, mod 5. All of them can be done with constant fixed memory or log time or log space. And any algorithm for which you can work with a single stack, right? A lot of service routines like depth first search, breadth first search, for which you just need one stack to move along. That is usually context free and represented using a push down automata. And anything beyond that, linear time, polynomial time algorithms, and intractable problems, all of them need Turing machines. So finite state automata form an interesting class because they represent algorithms that can be solved by logarithmic time, logarithmic space. It's a fairly wide class of algorithms, especially the kind of ones that are used in hardware circuits, parity checking, mod division, stuff like that, are all by finite state automata. Learning was introduced in the late 1980s. Learning regular languages, as I told you, helps you to develop algorithms to learn invariants for programs and software design and verify them. So what I'll do in this talk today is I'll introduce you to finite state automata very briefly. It's not meant to give an exhaustive introduction to what a finite state automaton is, but a brief introduction. We'll look at some examples, we'll solve some problems on the way, and then I'll look at automata learning, which involves learning regular languages. So here is an example of how a finite state automaton looks like. Can you help me to read this? How would you read this picture here, this graph here? What are the circles in the picture? They are states. And what are the directed edges? They are transitions. So there are two kinds of circles. There's a circle with an arrow coming in, and then there's a double lined circles. Right. So this is the initial state from which the machine begins its work. And this is a final state or an accepting state from where the machine ends its work, in the sense that if it finishes its work and ends up in that state, whatever it's ran through gets accepted. If it doesn't end up in that state, whatever it ran through doesn't get accepted. So that's how you read. So a finite state automaton has states. They're represented as circles. The state with an incoming arrow is the initial state from where computation begins. The state with two lines is the final state from where computation ends. Then you have transitions. How do transitions look like? They are directed edges that connect the states. Not only do the edges have directions, they also have labels. Labels come from an alphabet involving, just think of an alphabet as an abstraction of something that you don't want to know. So how do you read this? So from this state, on reading an A, you go to that state. From the initial state, on reading a B, there is a self loop which indicates you stay on there. I mean, you take a transition, but you come back to that state. That's what it means. Again, on reading a B in the final state, you go back to the same state. On reading an A, you come back here to this state, right? So this is an automaton that has two states, 4 transitions. Out of the 2 states, one is an initial state, one is a final state. So there is a notion of how this automaton works, or what does it do. So it always begins working by starting from its initial state. And then it uses its arrows to go out. Think of it like a traversal in the graph. Begin your traversal from the initial state, use an arrow to move out. So when you begin at an initial state, what are the 2 kinds of arrows you could use to move out? The transition that takes A, which goes into the other state, and the transition that takes B, which comes back into this state. So you could do one of those. So let's say you take, this doesn't seem interesting, right? Because it seems to come back here. So we don't want to do that. We don't want to do the work and come back to the same state. So let's try taking the transition that goes into the other state. So we read an A, go here, and you keep doing the same thing. You could stop saying, I finished. You could be lazy, just I read one A, you stop. So when you stop, what happens? Any idea? The single letter A that you have read, where did it take you? It took you to the final state, which means that the single letter A that you have read is accepted by the finite state automaton. You need not stop there. You could do more work. So from once you are in this state, what are your options? You could read another A, or you could read a B. So if you read a B, you stay on there. You could keep reading B's, you'll stay on there. So an A followed by any number of B's without an A in between will make you stay on in this state. If you read another A in between, you come back to the initial state. This state is not an accepting state, right? So some words that you read get accepted, some words that you read don't get accepted. So if you see the kind of behavior that this automaton exhibits, you see these states roughly as locations or memory entities that count the number of A's that you've read. If you are in this state, how many A's would you read to start with? To start with, how many A's would you read? 0. And then if you're come back to this state, how many A's would you have read? 2 or even 4, because you could do the thing again, or 6. In general, an even number of A's. Read that blue E as representing an even number of A's. Similarly, if you're in this state, how many A's would you have read? You could have read 1A to begin with. You would land up in this state. And then when again would you land up in this state? We're focusing only on the A's. So you could read 1 more and 1 more, right? That is 3 A's. Or you could read 1 more and 1 more. That is 5 A's. So in general, it is 1 plus 2 into n. So 2n plus 1 states. 2n plus 1 number of A's will take you to this state. That is, an odd number of A's will take the automaton to this state. An even number of A's will take the automaton to this state. So you think of this automaton as counting parity. In the letter that I have read so far, in the word that I am reading so far, am I reading an odd number of A's or am I reading an even number of A's? When we say parity, we mean odd or even. So if I'm reading an odd number of A's, I'm here. If I'm reading an even number of A's, I'm here. Per se, I don't care how many B's I read. This automaton doesn't really care. It allows you to read B, but it doesn't take a decision based on the number of B's or the pattern of B's that you read. So state E is the number of A's seen as even. State O represents the number of A's seen as odd. So what is the language accepted by this automaton? Can you tell me? All language means all words that take the automaton to the final state, which is that double circle state. What is the language accepted? It's okay to get it wrong, just make a guess. Set of all words that have an odd number of A's. Any word over A's and B's where the pattern is such that the number of A's is odd will make the automaton go in this state. And that state counts the number of A's as odd. Is this clear? So the language accepted by this automaton is the set of all words that have odd number of A's. So let's look at one more example. So here is a DFA that contains little more states. So it contains 4 states. The initial state is there, leftmost. The final state is here, rightmost. So what does it do? Again, in the initial state, it can read an A or a B. In all the states, it can read an A or a B. In the initial state, it seems to stay on there. If it reads an A, it moves out. In the next state, if it reads a B, it moves out. In the next state, if it reads a B, it moves out again, right? So which is the pattern that takes you? So if you have to trace a path from an initial state to an accept state, assuming that this is a graph, which is the pattern that helps you to take that path? A followed by B followed by B. You could do anything in between. You could begin with B, B, B any number of times, but you have to do 1A to move out, and then you could do any number of A's. You have to do 1 more B to move out. Move out meaning make progress towards moving to the final state, and then you have to do 1 more B to end up there. After that, you could do anything you want and stay on there. So this finite state automaton accepts any string that contains ABB as a substring. Is that clear? It contains ABB as a substring. So you understand the word string and substring. There is no confusion about that. String is just a sequence of letters. Substring is a part of that sequence. So how will I intuitively understand that this automaton is correct? What does the initial state represent? Read it as epsilon. In computation, when we say epsilon, we mean something that's empty. We like to talk about things that are empty. You might wonder why we want it. It's nice because it has nice algebraic properties. So this means that I've not seen anything so far. I've not seen ABB. That's the pattern I'm looking for. I've not seen that. And this means that I've seen an A in the string ABB that I'm looking for. That's the next state. The next state says that I've seen AB in the string ABB that I'm looking for. And finally, I've seen the whole thing, ABB. And then I accept. Anything in between works fine. Is this clear? So this is another finite state automata. So these are two simple finite state automatas. So in general, how do finite state automata work like? They always work on an alphabet in the sense that they have these transitions that are labeled by letters from the alphabet. They always read letters from the alphabet. We call the alphabet sometimes using capital A for alphabet, or sometimes using sigma. It's a finite set. Usually it is a binary alphabet, 0 or 1. Most of the time binary alphabet, not most of the time, all the time binary alphabet is enough. But sometimes for convenience we like to work with small other alphabets A, B, C, D, A1, A2. You always use 0 or 1 for binary, or small English lowercase letters A, B, C for alphabet. What is a string or a word over an alphabet? A lot like English. English has the alphabet A to Z, lowercase, uppercase. What is a word? You just put together letters from the alphabet, you form a word. Of course, we have words that have meaning and we have words that don't have meaning, but everything is a word, right? So the same thing. A word over an alphabet is just a finite sequence of letters. Suppose I have an alphabet A, B, C, a word can be thought of like this. Another word over the alphabet is A, C, C, B, B, another word. Any number of words you can think of. We also call them words as strings, because in computer science we use string data structure the same way. And we specifically like a word or a string that's empty. Empty in the sense it's just an empty word, like an empty set. So we always call that as epsilon. Some books might call it as lambda. It's the same thing. So what is a language? A language is just a set of words, a set of strings over an alphabet. So suppose I had an alphabet A language over that alphabet could be just a set containing 2 strings. Here is an example. It's just a set containing 2 strings. It's a language. We call it a language. Here is a larger language. Read these dot 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 as an infinite set. It contains all the words. Can you tell me the difference between these two languages? Can somebody explain what these two languages are? What is L2? What is L3? How will you read it? L2 is the empty language, the language that contains nothing. The language that contains nothing. That's also a language. What is L3? Yeah, L3 is a singleton set. It's a language that contains exactly one word. That word happens to be an empty word. Those two are different languages. L2 is a language that contains nothing. L3 is a language that contains a single word, which is the empty word. So you know how to define languages, right? So can you tell me what the language accepted by this DFA would be? I mean, we read it, we said it, but how will you write it like a set? How will you write the thing like a set? What is the alphabet? So how will you write the language that contains an odd number of A's? Will epsilon be in this language? Will the empty word be in this language? So empty word contains how many A's? So is 0 odd or even? Even. So 0 is even. So it will not be there in this set. Will the single letter A be there in this language? Yes, because there's one A, which is an odd number. So it will be there. Will AB be there in the language? Because it has one A, odd number of A's. It will be there in the language. Will BA be there in the language? Again, it has one A, odd number of A's, will be there in the language. Which will AA be there in the language? Because it has two A's. AAB? No. BAA? ABA? ABA? ABA will not be there, right? So what else will be there? All kinds of things. You're able to understand what I'm saying. So I can't put this. So what we usually do is we write set of all W for words, such that W contains, I'm writing the same thing, what I wrote first, in a slightly more mathematical notation, that's all. This is the language accepted by the automaton. Is this clear? I've written the same thing. It's English only. But the only other way to write it is to enumerate, which I can't do because it's infinite number of sets. So this is the language that is accepted by that automaton. So similarly, for every automaton, you can accept a language. Yeah. So this is how an automaton is defined in general. We work, I mean, there are things like deterministic automata, non-deterministic automata. I won't go into all that. We don't need all that. Assume that we work only with deterministic automata. Deterministic means in every state, on every letter in the alphabet, there is a transition out. So how will a deterministic automaton look like? It's basically everything is finite in this. Sets are finite. That's why it's called a finite state automaton. It has a finite set of states. Usually we use capital Q to denote the set of states. That's convention. Some books might use capital S. And then it has a distinct place to start. So that's called the start state or initial state. That's denoted by Q naught or S. Then it has a set of distinct places to end, which is also a subset of the set of states. That's the set of final states. How will you read this as? Read this as a transition function. What does it do? It takes a state and a letter from the alphabet. This is a cross product, Cartesian product of two sets, a state and a letter from the alphabet. That's how I denote it as Q cross A. And what does it give you? Another state. So it tells you from a state, on reading a letter from the alphabet, what is the resulting state. Is this clear? So Q cross A to Q. So that's just a function. So how will I read, for example, in this case? From this state E, on reading the letter A, I go to the state O. From the state E, on reading the letter B, I go back to the state E. From the state O, on reading the letter A, I go to state E, and so on. Right? So a transition is a function that takes a state, a letter from the alphabet, and returns another state. It returns another state. Right? It's just a function from Q cross A to Q. So yeah, so this is the same thing for that example. So this is the DFA that we saw earlier for odd number of A's. The set of states are two sets, E and O. Start state is this set E. Final state happens to be only one state here. In general, it could be an arbitrary subset. How will I read the delta transition? Just read out this graph. That's what is written here. Delta of E, comma A takes me to O. Delta of E, when it reads the B, takes me back to E. Delta of O, comma B takes me back to O. Delta of O, comma A takes me back to E. Right? So this is a finite state automaton. Yeah. So how does a DFA behave on a given word? So it always takes a word as input. It will take a word as input, and then basically it starts running on the word. So we use the word run. So what does it mean to say running on the word? Think of this like a graph and trace a path beginning at the initial state by taking the transitions that represent that word. So that's what is called a run. So I've defined it mathematically, but don't worry too much. So what it says is that, so set of all words is denoted by A star. So it says that if I have to read a word, I basically keep applying the transition function again and again. Basically it traces a path labeled by that word on the graph of the automaton. And if after reading the entire word, if the path ends up in a final state, then you say that the word is accepted, otherwise the word is rejected. So for odd number of A's, this is the language. You can go on and on and on. It's an infinite language. So we say a language is regular if there is a DFA such that it accepts that language. Otherwise the language is non-regular. Examples of regular languages that we saw, odd A's we saw. Yeah, a few other things are there. So I'll come back to that. Maybe before that, we'll do a small exercise to understand what a regular language looks like. So I'll give you a small problem. See if you can do it. So my alphabet is only binary words, 0, 1. Okay. And I want to accept a language you accept a binary word if its corresponding decimal representation is divisible by 3. So what is my possible words? Epsilon, 0. I'm just listing binary words. I'm not doing anything great here. 0, 0. I'm just listing binary words in the lexicographic ordering. Need not list them in lexicographic ordering, just list it. So what does this represent? What is the decimal number this represents? 0. Let's just list the decimal numbers. 1, this one. Okay. Okay. You understand, right? So these are the decimal numbers. So I'll accept a binary string if the corresponding decimal number is divisible by 3. Otherwise, I won't accept the binary string. Is the question clear? Can you design a DFA for this? So it reads binary strings. As it reads a string, it checks if it has potential to be a correct multiple of 3. So you divide the corresponding decimal number by 3. The remainder should be 0. Accept only those binary strings. Reject everything else. So let's try to draw a DFA. First part is very easy. Start state. We always need a place to start. It can only read what? It can read what are the two options that it can read? 0 or 1, because it works on a binary alphabet. So what does it do when it reads a 0? What does it do when it reads a 1? So how do you want to read it? Left to right, right to left? Read it left to right. It's okay. But remember, the number should be divisible by 3. So when you read it left to right, keep in mind the decimal number that you'll get for every bit that you read forward. So if the first bit, if the leftmost bit that you read is a 0, does it matter when it comes to divisibility by 3 or not? So then don't do anything. You're able to understand? Stay on there. It doesn't matter if the leading bit is a 0. The leftmost bit is a 0. I'm checking for divisibility by 3. The leftmost bit is a 0. Doesn't really influence divisibility by 3. So don't do anything. Stay on there. Suppose the leftmost bit that I read is a 1. It could be, it may not be. Look at the examples. If I had read the string 1, then I get a 1. If I had read 1, 0, then I get a 2. If I read 1, 0, 0, then I get 4. If I read 1, 0, 1, then I get a 5. None of them are divisible by 3. Sorry? But 0 is divisible by 3. Yeah, so what do? We'll come to that. 0, yeah. Yeah. So how many states will this automaton have? Exactly. You know why 3? You need another state to go to 1, right? So, but why 3? There's a different reason for 3. So I'll put this. You're right. Okay. So you're giving me more transitions. So what do I do here? Put a self loop on 0. Put a self loop on 0. If it's one more 1, you reach the final state. Okay. Then in the final state, then which is C and which is the third one? Yeah, back here, back on which one? On a 1. Okay. Finished. Okay. Any change? Not the self loop. Okay. So there's a small suggestion here. So we'll erase it and draw the suggestion again. So what are you saying? Is this correct? Okay. 0 will be accepted, right? If you make the first state the final state, 0 will be accepted. Do we need it to be accepted or not? Is this correct? No. Two final states, okay? That may not be right. We'll see anyway. So, okay, why 3 states? Any more reason? Why we're not going to the fourth state at all? Why? We seem to be happy. Nobody suggested that you put another new state. Yeah. Exactly. You understand why 3 states? You're checking for divisibility by what? 3. How many possible remainders are there? Divisibility by 3. How many remainders are there? 0 or 1 or 2. So what do these states keep track of? As I'm reading a binary string, keep the decimal number that you've got in mind in some sense and divide. Is the remainder seen so far 0? Is the remainder seen so far 1? Is the remainder seen so far 2? So based on that, you transition. So the final state should be the state that corresponds to remainder 0 only. So there's only one final state. So there cannot be two final states. So we've marked two final states. So let's remove one. Which one should we remove? The rightmost one, okay? So intuitively, what is your understanding? The state, I'll just write the number here. The state corresponds to remainder 0. The state corresponds to, if I divide the corresponding number by 3, the remainder will be 1. The state corresponds to the remainder being 2. That's the intuitive understanding. Can somebody do a final check of this automaton to see if it's working correct, or you need more changes? 3 states, okay, we seem to have settled. Are the transitions right? Take a number, take that 6, take 6 and take 9 and see, run it through the automaton to see if it accepts 6 and 9 and rejects 7. Yeah. Yeah. Yeah, so 0 is divisible by 3, trivially assume that. So it can handle 0, 0, 0, 0, all zeros. That's okay, with the assumption that it divides, 3 divides 0. Is this right? It's not working for 0, 1, 1. What is 0, 1, 1? 0, 1, 1 is 3. Okay. It's not working. Correct. 3 divides 3, so it better work. What is the change you'll make? This one? Where do you want to put it? Back here. Sorry, it's looking a little cluttered, but I hope you can read it. Is this work now? Huh? It's not each other. Yeah. So what do? State number 2 can't be reached at all. It's fully wrong. Try again. Because 3 has to be accepted. So the tweak was to accept 3. So let's try to accept 3, but in other ways. This fixed. No problem. Everybody agrees. 3 states. Final state is 0, right? Let's start all over again. 1. That part seems okay. 0 self loop. That part's probably not okay. That's also okay. 100% clear. Okay. Now 1 to 0 back on 1. Okay. This will accept 3. You're happy? Okay. Now? Okay. Are we done? Now you can do some testing, test cases. Run it on some positive examples What are positive examples? Binary strings whose decimal is divisible by 3. Run it on negative examples. What are negative examples? Binary strings whose decimal equivalent is not divisible by 3. Independently, in the theory of computation course, you have to give a proof that this is correct. Today, I won't worry you with that. Seems to be okay, right? It looks neat also. It's nice and symmetric, right? Because it seems to be very symmetric. So finite state automata can do mod 3. Can they do mod 4? Mod 5? Mod 17? Same logic. It just gets bigger and bigger. If it's mod 3, it'll have 3 states. Mod 17, it'll have 17 states. Mod 29, it'll have 29 states. Mod 4, it'll have 4 states. So you fix a number. If you want to do modulus that number for a binary string, finite state automaton can do it in a purely memory-less way, right? There's no stack, nothing, no memory, right? So finite state automata is very good for this. You are able to understand how a finite state automaton works. I hope there's no confusion, right, with this. So you can do mod 4 similarly. It just has 4 states. Mod 5 will have 5 states and so on. So they accept a lot of powerful languages. So they accept odd and even number of A's, which is parity. They can do mod division as we saw it with a fixed number. Then they can also do things like this. So the third, this part, the third language that you see here is written as strings that don't end inside a C style comment. So you may not be C programmers. When I learned programming, we learned only C and Pascal. But you know what a C program comment looks like? It has that slash and star and star and slash. So that's what it looks like. So this basically looks for strings that are not within comments, that are not inside comments. So why would this be useful? Why would we want to check for this? Why would, can you think of one kind of software or subject that looks for this? Compilers. So which is the step in compilers that does this kind of thing? Lexical analysis and parsing, right? Parsing. So what it says is parse but remove comments. So just keep them away. How do you identify comments? Use a finite state automaton to do it. Of course, you don't see it as a finite state automaton. You write a C compiler in C, you'd probably see it as a C program. But underlying, it is actually a finite state automaton. So finite state automaton can do memory-less parsing. But for normal parsing, you might need a PDA because you need a stack to do parsing. But this kind of parsing it can do. So what is this language? We saw this. This is also a regular language. What is this language? Yeah, empty language. That's a regular language. It accepts nothing. So what is the automaton for that language? If it's a regular language, you should give me an automaton for it. What is the automaton? Automaton should have states. It should have things around. What will be the automaton? Single state automaton. What will that single state be? Initial state, final state? Without any transition. Set of transitions is empty. That single state is the initial state. No final states. It doesn't move. Just that's it. So how will it look like? A circle with an incoming arrow. That's it. So suppose you want to accept the singleton language epsilon. What will the automaton look like? Make that single state a final state also. Start and begin there, end there. So that will accept the epsilon, singleton epsilon. If you want to accept empty sets, just single language. Why is any finite language a regular language? That's a sweeping comment. It says any finite set over sigma is a regular language. I don't know whether you've heard of this before in your automata course, but that's what it says. Any finite set over sigma is a regular language. If it's a finite set that has 100,000 symbols of random kind, it's a regular language. Yeah. What is a brute force automaton for a finite set? One path for every word. You're able to understand? I mean, you know the word brute force in algorithms. You do nothing clever. So what is a brute force automaton for a finite language? If a finite language has 100,000 words, have one path for every single word. I mean, you can't draw the automaton, you can't visualize it, but it's a regular language. It has finite number of states. So any finite language is a regular language. So there is a variety of regular languages. They are very powerful. So regular languages can represent programs that can do or parity checking, can represent programs that can do mod division, can represent programs that can do elementary memoryless parsing, a lot of other things, right? So they represent a useful class of programs. We don't see them as C programs or Java programs or anything like that, but they are programs. We just see them as finite state automata. But they represent a fairly large class of programs. So we want to be able to learn a program. What do we mean by learning a program as a regular language? Any thoughts, any discussions? Suppose I tell you learn a regular language, learn a finite state automata. That's the thing that we are moving on to next. What does it mean? What does it mean to learn? What would you expect as inputs? What would you expect to be given as output after the learning algorithm stops? So how will you produce the language as an output? Language is a set, right? So suppose it's an infinite set, you can't list the elements of the language. So if it's a finite set, maybe you could list the elements and produce it as an output. Correct. The result output of the learning algorithm is a language, regular language. How will you produce the language as an output? It's clearly cannot be represented as a set. Yeah, so you have to produce as output a representative for the language. So what is that representative? A regular expression could be a representative, but assume that we don't know regular expressions. That's a very correct representative. A grammar could be a representative. One more. We already saw the representative. The DFA. DFA is another representative. So give a DFA. Given one DFA of any kind, is everybody convinced that it accepts exactly one language? I mean, if two people think for one DFA it accepts two different languages, one of them is wrong. Is that clear? Given one DFA, it will represent exactly one regular language, right? So you could output the language as a DFA. The output of your learning algorithm that learns the regular language will be a DFA. It will output the DFA and say, see, the language accepted by this machine is the regular language you are trying to learn. What is the input to the learning algorithm? What kind of strings? Correct. What kind of strings? Input to the learning algorithm is strings. How many strings, in what order, and what kind of strings? It's okay to get it wrong, just think. Divisibility by 3. So you give string 0 as one input, then, and then you can give the string 1 1 as input. What is 1 1? Is it divisible by 3 or is it not? 1 1, the decimal equivalent of 1 1 is divisible by 3. Okay, 0 is also divisible by 3. 1 0. So what is 1 0? Is it divisible by 3 or is it not? Yeah, so what kind of strings? Can you generalize your answer? So you give strings. So there is a learning algorithm. That's the algorithm that we want to study. Its output is a regular language. What is its input? Set of strings. Yeah. Built over the alphabet. Any word or string built over the alphabet. Correct. So let's take that. So I want to learn. This is the algorithm that we're going to learn. What is its output? Output is a regular language. But I can't give a language. Why can't I give a language? I mean, as human beings, we can read a language, right? Set of all something, something. A machine can't read that. If it's an infinite set, a machine can't go on listing it. It will not terminate. So how will the language has to be given a representation, a computer representation, any valid representation, regular expression, a grammar. But for us, the representation would be a DFA. So it will give a regular language as a DFA. It will output a DFA. So what will be the input to the, by the way, this whole learning algorithm, I fix one input alphabet. I don't want to change this. Because if you change halfway through learning your alphabet, then there'll be confusion. So you fix an input alphabet. We always work with a fixed input alphabet. We don't change that. What is the input? So far the answers that have come is give a set of strings. This is what I want to do. Given a set of strings as input, I want to understand a learning algorithm that will learn by using this set of strings a language and say whether it is regular or not. Is this clear? So yeah, before we move on, just one more point I'd like to make, which is important for us, is the following. So there are languages that are not regular. Can you give me an example? Not every language is regular. We saw regular languages, some examples. Can you give? Correct. This is an example of a non-regular language. I won't go into the details of how to prove that it's non-regular and all that stuff. But how much ever hard you try, you cannot give a finite state written for this. You cannot do it. It's an example. There are uncountably many non-regular languages. There are countably many regular languages. So I'll just change this a bit. So I'll just change this a bit. What about this? Why? Because of finite set. So there are languages that are regular, there are languages that are not regular. Remember that. Oh God. So we'll go back to our, by the way, we will call it L star. That's the name Dana Anglin gave for it. So our learner is L star. So now we'll have to ponder over the input a bit. We'll have to elaborate. It's a set of strings, correct? But some more we need to talk about it. In general, in a learning algorithm, let's say artificial neural network, what would be the input? Something else? Not 3, not divisible by 3. Yeah, so what would be the training set? Training set is the input. What would be the training set? Yeah, it has to include a detail about whether the string is part of the language or not. So bits and pieces, you've said it. So we'll call it as so negative examples for the divisibility by 3 will include strings that are not divisible by 3. Positive examples will include strings that are divisible by 3, right? And then the output is a learner language, regular language. Is this clear? So this is how the learning algorithm will work. So it gets a set of strings, positive and negative. It has to learn a regular language. So this is played as a game between two entities, a teacher and a learner. So that's how it is given. So this is the person behind learning regular languages. That's the paper. It appeared in Information Computation 1987. Her name is Dana Anglin. So it's called Anglin's algorithm. Learning regular sets from queries and counter examples. Counter examples are what she means by negative examples. Right? It's very rare to get a result produced by a female computer scientist. So I took the trouble to put her photo so that you all remember that it's a result produced. But throughout this ML course, I wonder, given the 100 plus results that you would have learned, how many of them were authored by a female author? There'd be very few. There's very poor diversity in computer science. So I take pride in diversity. So that's why I took the trouble to put Dana's photo there. Right? So this is Anglin's algorithm. It's called L star algorithm. So there is a teacher and there is a learner. Learner is the one who's trying to learn the algorithm. Learn the regular language. The goal of the learner is to learn the regular language. And so the learner and the teacher talk to each other. So what do they talk? So the learner gives a word, a string, and asks the teacher. So the teacher knows the language in his mind. It's unknown to the learner, but the teacher knows it. So let's call the unknown language to the learner as U. The goal is that the learner is trying to learn the unknown language U. So the learner can ask the teacher questions. So learner can come up with a string, with a word, and ask for a membership query to the teacher. Does this word belong to the unknown language that you know, I don't know? The teacher will say yes or no. And the teacher is always correct. Teacher is not malicious and all that. Assume that the teacher is correct and consistent. The learner, at some point, to start with, the learner will take some words and keep asking membership queries, keep getting yes or no. Sooner or later, the learner has to figure out the unknown language U. At some point, the learner begins to converge on the language. So learner will say, okay, now I think I've come up with a language. So it'll give the language to the teacher and ask, is this language that I'm giving you equivalent to the unknown language that you have? Is this language the same as the unknown language that you have? That's what I mean by equivalent. Equivalent is normal equal to. There's no other equal. Teacher will say yes. Means what? We are done. Is that clear? If the teacher says yes, then the learner is finished learning the unknown language. You exit the process. But the learner could have got the language wrong. So in which case the teacher will say no. But then usually, as human beings, when you say yes, is my thing correct? And you say yes, everybody happy, no questions asked, go out. But if you give a program to your teacher and your teacher says wrong, you say, why? It's a natural question to ask, right? We don't want to be convinced. So the teacher is a good teacher. So he or she is just not going to say no. He will give a string as a counter example. So what would be that kind of a string? What would be a good counter example that the teacher could give? What kind of a string? A string that doesn't work, meaning what? Correct. Can you make the string that does not belong to the set that this one is conjectured? It belongs to the unknown language, but it does not belong to the set. So a string in the symmetric difference of these two languages. So the teacher will give a counter example when it says no. So is this clear? So this is the algorithm. The teacher has a unknown regular language U in mind. Is this clear? Learner can ask two types of queries to the teacher. Learner can give a string and ask, is this given string W in the unknown language? Teacher will say yes or no. For that, teacher doesn't give a counter example and all that. Is that clear? That doesn't make sense because it's just one string. You say yes, it's there. No, it's not there. That's all you can do. And the second kind of question that the learner can ask the teacher is, learner feels that he or she has already got the DFA for the language. So he gives the DFA to the teacher and says, is this the DFA that accepts the language that you know, that I don't know? Teacher will say yes, in which case we are done. The algorithm is over. We learned a language, we come out. Or the teacher could say no. The no will be a word that comes in the symmetric difference of the language given by the learner and the language that the teacher has in mind. Right? So Anglin's algorithm for the learner. So learner uses Anglin's algorithm. What does it find? It finds a canonical DFA for the unknown language U. And it's not a long drawn algorithm. It's not an algorithm that will not terminate and all that. It's a nice polynomial time algorithm. So what is the time that it takes? The number of steps that this algorithm will take is polynomial in the number of states of the canonical DFA for the unknown language and the length of the longest counter example returned by the teacher. What is the length of a string? What is the length of a string? Number of symbols. You just count the number of symbols. That's the length. So a counter example is a string. So you just count the number. So the Anglin's algorithm will terminate in polynomial time in these two factors. So what is a canonical DFA? Any thoughts? So we've used the term canonical. What is a canonical DFA? Something that's canonical. Any other word? Yeah. Yeah, it has a minimum number of states. Minimal, because there could be two equivalent. Yeah. So it is the least number of states. So it's not just random DFA, brute force DFA. It's a nice succinct minimal number of states. So is the overview of the algorithm clear? This is how the algorithm works. So we'll do one example and then we'll see the algorithm. Maybe I'll stop with the example and then we can take 10. What time is your coffee break? 10:45, right? Okay, so there is time, not 10:30. So here is an example. So let's say this is the unknown language. The unknown language U is given by, so by the way, yeah, are these steps clear, please? If this is not clear, there's no point in moving on. Is this clear? There is a teacher who knows the language. There is a learner who's trying to learn the language known by the teacher. Two kinds of questions the learner can ask the teacher. Give a word, ask if it belongs to the language. At some point, give a representation of the language, ask if that is the language. Teacher can say yes or no to both the answers. Here it's just a plain yes or no. Here if it's a no, the teacher gives a counter example also. The algorithm will terminate in polynomial time. So this is the language the teacher has in mind. Unknown language is the one that's given on top. Set of all words, the alphabet is A, B. Set of all words with number of A's even and number of B's even. You want to spend 2 minutes trying to draw the finite state automaton for that, just so that you know what it is. Even number of A's and even number of B's. You want to make an attempt to draw a finite state automaton for that? We can do it together. Number of A's and number of B's is even. Sorry, how do I go back to the next page? I lost it. Everybody can do this much. No problem. You have to count both A's and B's, the parity of A's and B's. So I've begun. Don't self loop on anything because A's are important, B's are also important. So don't put a self loop. Go out. You're able to understand? Please remember it's an and. So let's say I go out on reading an A. I go out on reading a B. With just this much that is drawn now, how many A's have I read and how many B's have I read? One. 1A, 1B. And what is it in terms of parity? Odd. So now what do I do? So the next A and the next B that I read will be 2, which in general could be even parity. So how will I do that? What would I do? That's another thing. To start with, I could read a A or a B. So after this, I could read after the first A, I could read another A or a B. And after the first B, I could read A or a B. Yeah. So if I read a A after reading the first A, it will try, correct? Or I could read a B after this. Don't put self loops. In this automaton, there may not be self loops because every A, every B that you read matters for parity, right? So if I read a B, I better go out because I have kept. So let's look at this. So I begin here. If I am in this state, I've read an odd number of A, 1A. If I read one more A, I go back. So if I'm after this, I could read a B, I come out. Then I've read an odd number of A's and an odd number of B's. At this state, you could again read an A or a B. What do you do? Maybe I'll let you think about it for a minute. Similarly, at this state down from where you reached after reading a B, you could read an A or a B. Here, you mean for this one? This one? This one? This one? Yeah, what do you want to do on reading a B here? Sorry? Do this? You want to do this? What will you lose if you do this? If you have a self loop at any point in time, can you count parity? Can you count at all with a self loop? You are able to understand in a self loop in a finite state automaton pretty much means that you don't care what happens on that letter. Or let me give you an analogy. We'll go back to my slides and sorry. Do you remember this one? It had odd number of A's. The example that we saw earlier, it had self loop on B's because I didn't care about the parity for B's. I didn't care about the count for B's, so I put self loop on B's. But I cared about the count for A's. I wanted to read an odd number of A's. You remember this example that we did? So suppose, okay, one simple question I ask you. I want to use the same automaton, but instead accept the language with even number of A's. Can you tell me what the change will be? I want to use the same automaton, but instead accept the language with even number of A's. Make E the final state. You understand what I'm saying? So this two-step loop is the underlying structure to count parity. So if I want even parity, make the count state where the count is even as the final state. If I want odd parity, make the state where the count is odd as the final state. In this case, I wanted odd parity. So you're able to understand whenever I do this, I'm counting as 2n, multiples of 2. I'm counting in multiples of 2. right? Which means what, 1 here and 1 to go back. Whenever I go back here, I have counted an exact multiple of 2, counted even number. Whenever I stop here, I have counted an exact multiple of 2 plus 1. I have counted 2n plus 1. So I have counted an odd number. So this is the structure for parity. And this counts parity for A's. I want to replicate this structure in the example that I have to count parity for both A's and B's to be even. So you have to replicate that structure. So this self loop will not work. Let's remove that. Yeah, correct. So now we know what to do, right? We saw in that. Correct. Excellent. Okay. Which is the final state? The start state is the final. Why will this work? Yeah. So let's take some positive examples, negative examples. I'll come to that. Yeah. So let's take some, sorry, this is a little cluttered, but what I meant here is that this is a final state. So let's take some positive examples, negative examples. This is a positive example of negative. Even number of A's, even number of B's. Can you trace the run of the automaton? Begin here, the start state, read an A, come back on the second A, read a B, go out, then read an A, come back on the second A to the same state, read a B, come back to the final state. It seems to work, right? What about this? Positive example. You can trace the run of the automaton, it will begin and end at the final state. What about this? Another positive example. You can trace the run, it should work. It won't accept. Is this clear? Won't accept. What about this word? Positive. 0 number of A's, which is even for us, and 4 B's. Positive. So now why did we choose this state as the final state? Any thoughts? Why not the other 3? Or which could be a possible other candidate for a final state? So we chose this as a final state. That's correct. Why not this? Why not this? Why not this? What do those represent? Remember that 2n and 2n plus 1 that we counted. Can you use that analogy? That's one correct reason. That represents epsilon, which needs to be accepted by my language because it has even number of A's, even number of B's, trivially. Any other reason? So, okay, if that is the only reason, what other state would also work as a final state? The remaining 3. Which would count even parity correctly? Which other state would count even parity? This one. Is everybody convinced? This will also count even parity? Will this also count even parity? For which letter? For A. For A only? Or for A and B? It will count even parity for A for sure. Will it count even parity for B also? Can I reach this state with an odd number of B's? You can. 1A, 1B. It doesn't even do it for A. So what does this state count? Odd A and odd B? Okay, so if I have to accept the set of all words that have an odd number of A's and an odd number of B's, then which would be a final state? If I have to accept this, so what are the 4 combination of languages that I can accept with the same finite state automation? Odd even for A or B. You got it? play around with your final states and you get 4 different languages. The underlying structure is the same, right? So these are regular languages. So the example that the learner wants to learn is that language, is this language. So the unknown language which the teacher knows, which the learner doesn't know, is that language. Set of all words in A comma B star. Read that A comma B star as set of all words over A comma B. Number of A's is even, number of B's is even. That's the language that we just did a finite state automaton for. Now the learner's job is to figure out that from scratch. Learner doesn't know anything. Teacher knows, black box kept hidden in the bag, right? So learner begins by asking queries. What are the 2 queries that the learner can ask? Give a word and ask, does this belong to the language? Learner's conservative, doesn't want to be ambitious. If you want to take the conservative approach, which is the word to begin with? You want to be very, very conservative, which is the word to begin with? Epsilon. Independently, it's a debatable question of how much will I learn about the language, whether epsilon belongs to it or not. It's a worth valid question, but it's all right. Begin with epsilon. So learner first gives epsilon to the teacher, asks, does this belong to the unknown language? Teacher says yes or no, right? If the teacher says yes, then the learner puts epsilon here and puts 1 to indicate that the answer is yes. If the teacher says no, then the learner will put a 0. Okay. After this, what is the next conservative step that the learner can ask? The learner is just giving letters, too early to guess a language. What is the next? Take single letters from the alphabet. Learner's being very, very cautious, very conservative, because he is to learn an unknown language. So which are the 2 single letters in this alphabet? It's a 2-letter alphabet, A and B. So the learner gives those 2 to the teacher, asks, is A in your language, B in your language? The teacher knows the language, you know the language the teacher knows. So what will the answer that the teacher give? No. No for A, no for B. Right? So learner says, okay, fine. He puts A here, puts a 0 because the teacher said it doesn't belong to the language, puts a B here, puts 0 because the teacher said it does not belong to the language. So the learner keeps giving strings to the teacher and asks questions. Teacher will say yes or no. So for every string that the learner gives the teacher, the string will be put here on this table, in this column, and then the answer that the teacher gives, if it's a yes, a 1 will be put here. If it's a no, a 0 will be put. So the learner builds this table, right? The table that the learner builds is called an observation table. So learner first asks the teacher if epsilon, A and B belong to you, and it obtains the following observation table. So there are also some more colors and things marked in the table. So there is this red S, and then there is this blue S concatenated with A comma B. So the set of strings S represents the states of the automaton constructed by the learner. I'll tell you why. An entry S comma E in the table represents the fact that from a state S, the automaton accepts or rejects the string E. We'll come back to this. Just one more point. Do you know what the symbol dot means in computation, theory of computation? Any guesses? Sorry, there were some whispers. It's all right. Just be loud. Huh? Concatenation. Okay, so we'll just understand concatenation quickly. In layman's terms, this is what it means. Put one after the other. That's what concatenation means. So suppose I have a letter A and a letter B. A dot B means put B after A. So this means don't take the trouble to write A dot all the time. It's too much. So just write it AB, right? So suppose I had the word AB and then the letter B. So if I concatenate A dot B with B, I get AB. Right? It just means put one after the other. That's all it means. Right? So in general, I could have a word W1 and another word W2. If I concatenate W1 and W2, I just put W1 after W, right? Please remember that dot, so we use dot to represent concatenation as an operator is not, you remember commutativity, associativity, basic algebraic operations, not commutative. The order in which you concatenate matters. So W1 into W2 is not equivalent to W2 into W1. It goes in an order, stays there, right? It doesn't change the order. So that's what this dot here represents. The dot here represents the set S concatenated with A comma B. If I concatenate A with epsilon, what will I get? A back again. That's what is written here. If I concatenate B with epsilon, I'll get B back again. So this set A comma B is nothing but this set S concatenated with A comma B. Is this clear? So far it's okay. Do you think the learner has enough information to? So the learner at some point has to begin constructing an automaton because its output, right, is going to be an automaton for the language. So these are the initial steps for the automaton. It says that the states represent, the set S represents the states and an entry S comma E. So which means what, from a state corresponding roughly to epsilon, on reading a 1, go back to the state epsilon. That's what it means roughly. So far, it's only 3 strings and it's not yet got any information. So what is the next conservative string that the learner can give to the teacher to ask? It could be AA or AB or BA or BB. Strings of length 2, right? So there's no hard or fast rule about what it gives. Yeah, so I'll come back to that. So the learner just asks the teacher just two out of those 4 choices. It gives AA and AB, only those 2 letters. It had 4 choices for words of length 2. So it says AA and AB. So which is a positive and which is a negative example? The learner doesn't know that. Only after the teacher gives the reply will the learner know. A is a positive example, so the answer from the teacher will be a yes. AB is a negative example, so the answer from the teacher will be a no, right? So the learner says, fine, I gave AA, teacher said yes, so I put a 1. I gave AB, teacher said no, so I put a 0. So it builds the table, right? So far it's okay, right? So can you tell me a difference between the previous table and this table? 2 rows have been added. Any other change? I'll just put back the previous table. That's the previous table. This is the next table. 2 rows have added. I've made one more change. Yeah, something has gone up to the set S. Earlier, the set S was just epsilon. Now the set S has become A also. Why? Any thoughts so far with what we know so far? Any thoughts? What do you mean all the combination with prefix A? You're probably right. Can you elaborate that a little bit? All with prefix A. So there is this has a prefix A, this has a prefix A, this also has a prefix A. So what is true about those strings? Yeah, so far, yeah. So how do I interpret zeros and ones here? What do zeros and ones represent? 0 means words that are not there in the language. 1 means words that are in the language. So it seems to say that this is there and that's there. The rest are not there. So there is an important part about the prefix. So we'll come to that. There is why did I not put the line here? Why did I not move B into the set S? It's adding state by state, yes, but why did it not move B into the set S? Just, going to transit one by one, but why did it not read B and postpone A next time? I'm just, okay, let me put it different way. So it asks membership queries for AA and AB, right, up there. So what were the two other options for it? It could have asked membership queries for which are the two strings of length 2, BA and BB. Had it asked membership queries for those two, would the table look the same? What would have moved into the set S? B could have moved into the set S. It's just that the learner is unaware of what the unknown language is. Going by, it conservatively asks membership queries. So for the membership queries that is asked so far, this is true. So with reference to the membership queries, that prefix closeness is correct. Right. So we'll stop here. We'll continue with the algorithm after the coffee break.